Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of this lecture is Power Law and Ellis Model Fluids Flow Through Pipes. So, before going into the details of today's lecture, what we will do, we will have a kind of recapitulation of what we have studied in the last class. In the last class, what we have discussed how to develop the velocity profile for a time independent non-Newtonian fluid, or specifically in the case of power law fluids flowing through a pipe, circular pipe. That is what we have seen. So, we have a recapitulation of that one. In the previous class, we have seen the flow of power law fluids through circular tubes due to pressure difference if it is taking place. So, how to obtain the velocity profile, how to obtain the volumetric flow rate, how to obtain the average and maximum velocity, etc. Those things we have discussed, right. So, that what we got first by simplifying the equations of continuity and then momentum, what we got a few information about the pressure distribution and then relation between pressure and then shear stress, etc. Then we realized that for the case of flow through circular tubes due to the pressure difference, the shear stress that we got it as tau Rz is equals to minus delta P by L R by 2. Remember, till this point we did not incorporated any information regarding the rheology of the fluids, right. So, that means any fluid that is flowing through a pipe due to the pressure difference, then shear stress can be related with this particular expression irrespective of the rheology of the fluid. That is what we can understand. And remember, all that analysis whatever we have done in the previous class is for one dimensional motion, where only Vz component of velocity is existing and that Vz is function of r, right. So, for such conditions shear stress is a linear function of pressure gradient, and then the shear stress is 0 at the center and then it maximum at the wall, and then between these two limits of r is equals to 0 and then r is equals to capital R, shear stress linearly increases. And then wall shear stress, that is the maximum shear stress that you wanted to find out, you have to substitute small r is equals to capital R, that we get this one. Then after this, in this equation what we have done, we have substituted for tau Rz power law fluid. For power law fluid, tau Rz is equals to m minus dVz by dr whole power n, that is what we know, and then that we substituted in this expression and then simplified, then applied boundary conditions to get the velocity profile like this. Once getting the velocity profile, what we have done, we got the volumetric flow rate and then that is given by this expression. Then we got wall shear rate is nothing but 4 cube by pi r cube 3n plus 1 by 4n, this is what we got. Then average and then maximum velocity expressions we got like this. This is what we have seen, right. But whenever there is a fluid flowing through pipes, so then what is that important engineering property that you would prefer to measure when especially there is only momentum transfer, and then obviously what is that property that you would prefer to have the information about is the pressure difference or pressure gradient versus volumetric flow rate information, that is what you get. Also in addition, you try to have the information what is the friction factor. This is one of the very important information required for the designing of this, wherever this pipe information, connecting pipes, straight pipes, etc. are there. So, then this friction factor is very essential factor that one should have for the design as well as controlling the operational parameters. So, that friction factor we will try to measure for the case of power law fluids flowing through circular pipes, right. Friction factor, when Newtonian fluid flowing through circular pipes and then flow is under the laminar flow condition, then what we know, friction factor F is equals to 16 by Re, that we know. So, what is that we are going to have for the power law fluids case, that we are going to do now in today's class. So, friction factor, how we can define? We can define like dimensionless wall shear stress, that is wall shear stress non-dimensionalized using the kinetic energy of rho v square, because this friction factor is essential when the fluid is under motion. Okay. So, this F is equals to tau w by half rho v square is the definition that we can have. So, then now this F friction factor we have to find out for the case of power law fluids. Here this V is nothing but the average velocity and then tau w is nothing but the wall shear stress, that is minus delta P by L R by 2 or minus delta P by L D by 4. Now, for Newtonian fluids, we already know that this F is equals to 16 by Re, that we have derived in our basic fluid mechanics course, or basic transport phenomena course, right. Now, what is this if the fluid is non-Newtonian fluid, especially if the fluid is power law fluid, what is this F factor that we are going to see now. So, from this definition, equation number 15, what we have, tau W by half rho V square. Here in place of tau W, we can write minus delta P by L D by 4 and then divided by half rho V average square. This equation, if you rearrange, you can write minus delta P by L is equals to 2F rho V average square by D, right. So, now if you delta P, that is applied pressure difference, that dl, that is geometry of the pipe, that length, and then dimensions of the pipe, that is length and diameter, etc. Density of the fluid also If you know the average velocity, then you can find out the friction factor, right. So, in the previous lecture, we obtained the average velocity for a power law fluid flowing through circular tube. So, that is nothing but this, right, n by 3 n plus 1 multiplied by minus delta P R by 2 Lm whole power 1 by n R, right. So, now what we do here, whatever minus delta P by L is there in this expression, in place of minus delta P by L, we are going to write 2F rho V average square divided by D. When you write it is this one, this is what you get. So, this R also, what I am trying to do, I am trying to write it as D by 2. So, D by 2 and then there is already 2. So, D by 4 m, and then in place of minus delta P by L, 2F rho V average square by D, and then this is all under whole power 1 by n, and then this R is also D by 2 I am writing. So, this D is cancelled out, this 2, and then 2 1 ja 2 2 ja. So, this is what we get. So, what we do, this expression further you simplify, you get this equation, right. What we have done, whatever the F rho, that whole power 1 by n is there, then we expanded or individually we have written like F power 1 by n, rho power 1 by n, V average square power 1 by n. So, that is V average power 2 by n divided by 2 power 1 by n, m power 1 by n we are having, and then this D by 2 as it is. Now, out of this, what I am trying to do, I am trying to take this constant n by 3 n plus 1 to the left hand side. So, that I have 3 n plus 1 by n, and then this V average I will bring into the right hand side and then combine with this V average. So, that I have V average power 2 by n minus 1, that is 2 minus n by n. What I am trying to do further, I am trying to join this 2 power 1 by n and then 2, so that I can have 2 power n plus 1 by n. Now, if I keep only f power 1 by n one side and then all other terms to the other side, then I have this term, right. Then next step, both sides I am trying to do whole power n. So, then left side I have f, that right side I have 3 n plus 1 by n whole power n, 2 power n plus 1 m rho V average power 2 minus n d power n, right. So, this 3 n plus 1 by 4 n is a common factor that we get in general for shear rate expressions, whatever we have seen previously also when we are talking about the capillary viscometer. So, then what I am trying to do next step, I am trying to multiply this term by 4 power n and then divide the term right side by 4 power n. So, that I can write this f is equals to 3 n plus 1 by 4 n whole power n, 4 power n, and then remaining terms are as it is. Next step, what I am trying to do, I am trying to write this 4 as 2 square. So, that 4 power n I can write 2 power 2 n. So, that 2 power 2 n is combined with 2 power n plus 1, I can have 2 power 3 n plus 1, and then all other terms are same as it is, and then this m I am taking to the denominator here like this, right. So, now next step what I am trying to do, I am trying to multiply this expression by 16 and then divide by 16. So, that 16 by 16 and then all this as it is. So, now in the next step what I try to do, I keep this 16 as it is, and wherever the denominator 16 is there, that I will take to the numerator and then write it as 2 power minus 4. When I write it, then what I get, 2 power minus 4 and then 16 is here as it is. So, then this term is as it is. So, this term I can write it as, when you join these two terms, we can write it as 2 power 3 n minus 3, that is 2 power 3 n minus 1. So, 2 power 3 I can write as a 8. So, then what I can have, this term 16 divided by rho V average power 2 minus n d power n divided by 8 power n minus 1 m 3 n plus 1 by 4 n whole power n. So, now this is in a form F is equals to 16 by Re form. For Newtonian case, friction factor F is equals to 16 by Re, that form we have written for the case of power law fluids. So, by analogy, what we can write, whatever this denominator, this thing is their expression, that entire thing we can write it as Re for power law fluid. So, then we are writing RePL. So, RePL is nothing but rho V average power 2 minus n d power n divided by 8 power n minus 1 m 3 n plus 1 by 4 n power n. So, this RePL expression whatever is given is also same as given by the Metzner and Reed. So, it is also written as ReMR in some books. So, then what we have, if you write this ReMR or RePL in the form like rho V average d by mu effective in terms of mu effective, because we know that for non-Newtonian fluids the viscosity changes. So, which viscosity should you take? So, in that way if you write it as in place of viscosity, you are simply writing viscosity, because if viscosity is changing, Reynolds number would also be changing. So, rather writing changing viscosity with shear rate, if you write effective viscosity in the definition of the Reynolds number, then what should be that effective viscosity? That should be nothing but m 8 V average by d whole power n minus 1 3 n plus 1 by 4 n whole power n. This 8 V average by d is nothing but the nominal shear rate or true shear rate for the Newtonian case, and then nominal or apparent shear rate for the case of non-Newtonian fluids, that we have already seen in the case of capillary viscometers. Fine. So, this is what about the friction factor for a power law fluid flowing through circular tubes, right. So, now what we do, we take a different type of fluid flowing through circular tubes, but again due to the pressure difference. So, that means whatever previous lecture that we have taken a circular tube, infinitely long cylindrical tube, right. So, that is L by D ratio is very large. So, then we have taken only the fully developed region, or we have taken L by D very large, so that we have a fully developed flow. So, that if you have a fully developed flow, the analysis would be easy for you, that is in the flow direction the velocity profile will not change. Let us say if this is your r direction, if this is z direction, so then what you have, the flow direction only Vz you are having, and that is function of r. So, that velocity profile, if it is Newtonian fluid, then so if it is a Newtonian fluid, the velocity profile is parabolic like this, which we have already seen in the previous lecture, and then depending on the non-Newtonian behavior or the power law index, the profile changes. It becomes flatter for shear thinning fluids, and then it becomes very steeper, sharp kind of thing for shear thickening fluid, that we have seen, right. So, and then shear stress is linearly increases with r. Okay. So, that is what we have seen. So, all those conditions are same here again. Only thing that only change that we are going to have here, in place of power law fluid, now we are taking Ellis model fluid, right. So, the pressure at the inlet Z is equals to 0 is nothing but P naught, at the pressure at Z is equals to L is nothing but PL, and then because of this pressure difference the flow is taking place. And then all this analysis whatever we have done in the previous lecture, and then whatever we are going to do today's lecture, that is only for the fully developed region. It is not valid for the entry region or exit region. Okay. So, fully developed flow you can have when you have L by D is very large, so, right. So, since compared to the previous lecture everything is same except the fluid. So, then what we have, we quickly go through the initial constraints, assumptions, etc., simplifying of continuity equation, momentum equations, etc., quickly, because they are going to remain same, they are not going to change. The change compared to the previous lecture for the case of power law fluid will occur only from the point where you get this expression tau Rz is equals to minus delta P by L R by 2. So, till getting this point you are going to have exactly the same thing whatever we have done for the case of power law fluids in the previous lecture, right. So, but however, since we are in the beginning of solving such kind of problem, we will do once again. Okay. So, how we do? We first list out all the assumptions or constraints of the problem, then based on those constraints we are going to simplify the continuity and then momentum equations, and then from those simplified continuity and momentum equation you may be getting some relations. Using those relations you may get the velocity profile. So, that process is standard process, so that we are going to follow here also. So, assumptions, we have taken infinitely long cylindrical tube, that is L by D is very large, and then flow is laminar and incompressible. We are not considering gravity, we are not considering non-isothermal conditions, flow is isothermal. Then steady state, and then symmetric in theta direction, and then fully developed flow, that is what we have taken. And then in addition to that, what we have only Vz component of velocity, and then that Vz component of velocity is varying in the radial direction, r direction, right. V theta, Vz, V theta, Vr may also be there some values, but their magnitude wise they are very much small, compared to the Vz, and then especially in the radial direction they may be very small. Okay. So, compared to the Vz, V theta, Vr are negligible, that is what the basic bottom line. Okay. So, now these are same as previous class. So, then we are going to apply these constraints to continuity and then momentum equation. So, continuity equation, steady state. So, this is 0, and then Vr is not existing or it is 0, V theta is not existing or it is 0, r by symmetry also this term is 0. And then since fully developed flow, dou by dou z of any flow variable is 0. So, then continuity is satisfied. So, continuity is satisfied. Then equation of motion, r component of equation of motion is this one. So, steady state, this term is 0, Vr is 0, V theta is 0, and then because of the symmetry dou by dou theta of anything is 0, and then V theta is 0, Vz is there, but Vz is not function of z, is function of r only, and then Vr is 0, and then because of fully developed flow also this term is 0. Pressure we cannot say, pressures in general we do not have any generalized boundary conditions. Okay. So, we just leave it as it is. This term tau Rr would be having only Vr terms which is not there, and then because of the symmetry this term is 0. This tau theta theta also would be having only V theta term, so then it will be 0, and then because of the fully developed flow dou by dou z of any flow variable is 0. So, this is 0, and then gravity we are not considering. Also only tau Rz is existing in the current flow conditions whatever we have taken. So, all other terms of shear stress are 0. So, what we get here? We get dou p by dou r is equals to 0, that means pressure is not function of r. Similarly, theta component of momentum equation if you simplify, steady state. So, this term is 0, Vr is not existing, V theta is not existing, and then because of the symmetry this term is also 0. So, Vr, V theta both of them are 0, Vz is not 0, but because of the fully developed flow dou by dou z of any flow variable is 0. Fully developed flow in this case flow is in z direction. So, dou by dou z of any flow variable is 0, that is only for the flow variables, not for the scalars like pressure and temperature, right. So, the symmetry boundary conditions also in general only for flow conditions only, not for the scalars, temperature profile, pressure profile we cannot generalize. Okay. So, let us keep it as it is. So, tau r theta is having V r V theta terms, or this tau r shear stress tau r theta component is not existing. Because of symmetry, this term is 0. Because of the fully developed flow, dou by dou z of any flow variable is 0. So, this is 0, and then for laminar flow these two are equal to each other. So, that is 0. So, gravity finally we are not taking anyway. Then what we get here again, we get dou p by dou theta is equals to 0. That means p is also not function of theta. So, that means till now what we understand, p is not function of r and theta it is. So, but the flow problem is taking place because of the pressure difference. So, that what we can understand now from here itself, without solving the problem further, we can realize that p is function of z. What function, is it a linear, non-linear, that we do not know, that we can understand by simplifying z component of momentum equation. So, here steady state, this is 0, V r is 0, V theta is 0, symmetry. So, this term is also 0. V z is existing, but it is fully developed flow. So, dou by dou z of V z is 0. Pressure, you cannot say anything, any generalized conditions you cannot have. So, dou p by dou z we cannot cancel out. So, only shear stress is existing tau r z. So, which is again function of r, because in the radial direction only the shear stress variations are there, because the flow direction we are taking in the z direction. So, only tau r z shear stress component is existing. So, we cannot cancel out this term, and then because of the symmetry this term is 0, because of the fully developed flow this term is 0, and we are not taking any gravity in this problem. So, what we have? We have only these two terms. That means dou p by dou z is equals to 1 by r, dou by dou r tau r z, that is what we are having. Now, what we see here? So, left hand side dou p by dou z is there. So, already we realized by simplifying r and theta component equations, what we understand, that pressure is not function of r and theta. So, whereas the right hand side what we have, it is everything function of r, right. So, what we can say, this dou p by dou z is independent of whatever this thing is there in the right hand side, okay. And then similarly, the tau r z is function of r, because V z component should be there. So, the V z is function of r only. So, it is not function of z. So, whatever the right hand side terms are there, tau r z etc., they are independent of z. So, then what we say, for the right hand side term, whatever the left hand side terms are constants, they are not going to affect it, because left hand side term is only function of z, and then right hand side terms are only function of r. So, what we can do, we can individually integrate them. When we integrate, we get p is equals to C1z plus C naught. So, what are the boundary conditions? At z is equals to 0, p is equals to p naught. So, C naught should be p naught, and at z is equals to L, p is equals to p L. So, that p L is equals to C1 L plus C naught, then C1 we get p L minus p naught by L. That means, p is equals to C1 is p L minus p naught by L, z plus p naught. So, the same thing we can write, p L minus p naught we can write minus p naught minus p L and then divided by L. So, that p is equals to minus delta p by L z plus p naught. So, dou p by dou z is equals to C1 is equals to minus delta p by L, that is what we can write. Now, what we can do, whatever the dou p by dou z is equals to 1 by r, dou by dou r of r tau r z equation was there by simplifying the z component of momentum equation. So, we treat dou p by dou z as a constant for integrating the right hand side term. So, then what we do, r we take to the other side. So, then r dp by dz is equals to d by dr of r tau r z. So, now if you integrate with respect to r, so then what we have, r tau r z is equals to r square by 2 dp by dz plus C2, then that means tau r z is equals to r by 2 dp by dz plus C2 by r, right. And then shear stress cannot be infinite at any location between any value of r between 0 to capital R. So, but if you substitute r is equals to 0 here, this tau r z becoming infinite, which is not possible. So, then C2 has to be 0. So, that means tau r z is nothing but minus delta p by L r by 2. This is what we get, right. So, if you need to know the shear stress at wall, you have to substitute R is equals to capital L. R is equals to capital R, you have to substitute, then we get tau W is equals to minus delta P by L capital R by 2. So, what we do next? We try to obtain velocity profile for LS model fluid. Remember, till this point before this slide, we did not brought any information about the rheology of the fluid. So, till the point tau Rz is equals to minus delta P by L R by 2, that expression derivation, the problem is same if the flow is taking place in circular tube under fully developed flow conditions, right. So, now after this point we are going to bring in the effect of the fluid rheology. So, for LS model fluid, apparent viscosity is nothing but this is apparent viscosity. At the beginning itself we have made a generalization that if it is a non-Newtonian fluid, then whether you specifically write apparent viscosity or not, it is apparent viscosity, because viscosity changes with the shear rate. Okay. So, now this apparent viscosity is nothing but mu naught by 1 plus tau yx divided by tau of whole power alpha minus 1. Alpha is something like same like a power law behavior index for the case of power law fluid, but only thing that in the power law fluids, power law behavior index n is less than 1 for the shear thinning fluids, whereas in the case of LS model fluid this alpha is greater than 1. Okay. So, that is the difference, but the nature wise they are same. Okay. And this mu naught is nothing but 0 shear viscosity. This tau y of is nothing but let us say if your mu naught is 100 Pascal second. So, what is the shear stress at which this viscosity is becoming 50 Pascal seconds? That shear stress we call it as tau of. Okay. So, this we already know. So, that means in if you plot this apparent viscosity mu apparent versus tau yx, then this usually high it is large at the 0 smaller shear stress and then gradually decreases something like this. So, this is nothing but your mu naught, right. So, this let us say if it is 100, at what shear stress it is becoming 50, that mu naught is decreasing to half of its value. So, that value is known as the corresponding shear stress value is known as the tau of. And then we know we have already studied this LS model fluid is important when the deviation from the power law fluid is more at low shear rate range. At low shear rate range, if the deviation from the power law behavior is more important, so then it is better to use the LS model fluid for reliable information. Okay. And then such cases occur in general in most of the dairy products. So, the same equation if you write for if you write in cylindrical coordinates, then you have mu naught divided by 1 plus tau Rz divided by tau of whole power alpha minus 1. So, then tau Rz, tau is nothing but apparent viscosity multiplied by the shear rate, right. Now, shear rate is minus dVz by dr, and then in case only tau Rz shear stress component is existing. So, tau Rz is equals to mu naught divided by 1 plus tau Rz by tau of whole power alpha minus 1 multiplied by minus dVz by dr. So, now what we do? We keep minus dVz by dr one side. So, then remaining terms to the other side, what we have tau Rz plus tau Rz power alpha divided by tau of power alpha minus 1, and then this entire multiplied by 1 by mu naught. So, this minus if you take to the right hand side minus 1 by mu naught, and then in place of tau Rz you can write minus delta P by L R by 2, because that is just now we derived. So, when you write you get this expression, right. So, now if you integrate this equation, Vz is equals to minus 1 by mu naught minus delta P by L R square by 2, and then 1 by 2 is also already there. So, R square by 4 plus 1 by tau of power alpha minus 1 minus delta P by 2L power alpha, and then integration of r power alpha is nothing but r power alpha plus 1 by alpha plus 1 and then integration constant c. So, now that c constant, if you wanted to find out, the velocity Vz is 0 at wall, that is at r is equals to capital R, because of the no slip velocity is 0. So, that you substitute here in this equation. So, then you get this c constant, and that c constant you back substitute here, you will get this expression. So, this c constant is this one. When you substitute r is equals to capital R in the previous equation, then Vz will become 0, and then corresponding c is this equation, and then that c we are substituting in this Vz expression. Vz is equals to minus 1 by mu naught minus delta p by L r square by 4 plus 1 by tau of power alpha minus 1 minus delta p by 2 L power alpha r power alpha plus 1 by alpha plus 1 plus c, in place of c this is coming out. So, what we do, r powers whatever the similarities are there, those terms we combine together, that is r square terms we combine together, and then r power alpha plus 1 terms we combine together, then we get Vz is equals to this expression. This is nothing but the velocity profile, right. So, now this same expression, what you can write, minus delta p by L capital R by 2, you can write it as tau w. So, tau w, so 1 r is remaining r, and then divided by, in place of 4 we 2 is combined with the tau w. So, 2 is remaining. So, r by 2 mu naught multiplied by 1 minus r square by capital R square. Similarly, here also if we do, this is what we get, wherever minus delta p by L capital R by 2 is there, we are writing tau w here also. So, this is the velocity profile you get, right. Now, if you wanted to find out the maximum velocity Vz max, what you do, you can get by substituting r is equals to 0. At the center the velocity is going to maximum. So, when you substitute small r is equals to 0, then Vz is equals to Vz max, and then that is given by this expression. So, we got the velocity profile, we also got the maximum velocity now. Next, what we try to do, we try to get the volumetric flow rate. So, volumetric flow rate is q is equals to integral 0 to 2 pi integral 0 to r Vz r dr d theta. So, volumetric flow rate q is equals to integral 0 to 2 pi integral 0 to r Vz r dr d theta, but in theta direction we have the symmetric flow. So, then what we can have, 2 pi integral 0 to r Vz r dr, and then this Vz is nothing but this expression, just now we got it. I have written the expression before converting that expression Vz expression in terms of tau w. Okay. So, that Vz we are going to substitute here. So, then we have this expression. Now, what we can do, we can bring this r within the parenthesis here and then here also, and then do the integration. So, then we have this expression. So, here for the first case 2 1 ja 2 2 ja, and rest r square by 2 minus r power 4 by 4 r square, and then here again r square by 2 minus r power alpha plus 2 is there, integration of r power alpha plus 2 would be r power alpha plus 3 divided by alpha plus 3 will be having, right. Now, this lower limit is anyway 0. So, then you do not need to worry of substituting it, because all the terms are having small r values, small r's. Okay. So, now upper limit, when you substitute capital R, then you get this one. So, if you do further simplification, then what you get, q is equals to this expression. In the next step, what we can do, you can do LCM of this one. So, then you get alpha plus 3 minus 2 divided by 2 alpha plus 3. So, that is alpha plus 1 you get. So, that alpha plus 1 and this alpha plus 1 would be cancelled out, right. Then you have this term, right, this alpha plus 1, that alpha plus 1 is cancelled out and divided by 2 alpha plus 3 is there. So, that 2 and then this 2 pi 2 we can cancel out. Okay. So, this is what you get this expression. Now, again in place of minus delta p by L capital R by 2, you can write tau w, right. When you write it, you get this expression, q is equals to pi r cube divided by 4 mu naught tau w multiplied by 1 plus tau w by tau of whole power alpha minus 1 4 by alpha plus 3. This is what you have. right. So, if volumetric flow rate is known, average velocity can be found out by dividing the volumetric flow rate by cross section area of the pipe. So, pi r square q by pi r square, if you do, you get tau w r by 4 mu naught multiplied by 1 plus tau w by tau of whole power alpha minus 1 4 by alpha plus 3. This is what the average velocity. So, now we got the volumetric flow rate, average velocity as well, in addition to the velocity distribution and then maximum velocity. So, everything we almost everything we got except the friction factor. So, we try to do some simplification to get the friction factor as well. So, friction factor, we know that F is equals to tau w by half rho v square. So, now tau w is equals to half rho v square by 2. So, then what we do in place of tau w in the average velocity expression, we are going to write F rho v square by 2 from here. Then we get V is equals to R by 4 mu naught multiplied by tau w, that is F rho v square by 2 plus 4 R by 4 mu naught alpha plus 3 alpha plus 3 tau of power alpha minus 1 multiplied by tau w power alpha minus 1 multiplied by tau w, that is tau w power alpha, and then tau w is nothing but F rho v square by 2 power alpha is as it is, right. So, now next step what I am trying to do, I am trying to write this expression R also I am writing in terms of d by 2, so that we can define Reynolds number. So, then we have here first term in the right hand side dv rho by mu naught f v by 16 plus second term f power alpha, then rho power alpha, v power 2 alpha, etc. are there. So, then how I am writing rho power alpha, v power alpha, d power alpha, and then remaining v power alpha whatever is there. So, that I am writing separately, because here what you have only one d. So, d power alpha you have written here. So, d power 1 minus alpha I am writing here, and then divided by 2 mu naught power 1 minus alpha I am writing, and then whatever the mu naught is there I am writing mu naught power 1 minus alpha and then mu naught power alpha, remaining constants are as it is, right. So, this 2 power alpha is as it is, right. So, next step what I am trying to do, write dv rho by mu naught within parenthesis here, and then in the second terms also dv rho by mu naught power alpha here in the as a parenthesis within the parenthesis I am writing, so that I can write dv rho by mu naught, I can write it as a Re, that I can write. So, first term f Re by 16 I can have, second term f power alpha Re power alpha, and then remaining terms whatever are there v power alpha minus 1, d power 1 minus alpha, mu naught power 1 minus alpha, tau of power alpha minus 1, I can write it as v mu naught divided by t tau of whole power alpha minus 1, and then remaining constants 1 by alpha plus 3 2 power alpha plus 1, right. Next step what we are going to do, we are going to multiply 16 by Re both sides, because just wanted to write this also in the Newtonian case, like in the Newtonian case f is equals to 16 by Re form is there. So, that way we are trying to write. So, that is the reason I am writing, I am multiplying this equation both sides by 16 by Re. So, right hand side first term is f, and then second term 16 by Re, 16 I am writing as 2 power 4, and then Re power alpha divided by Re I am writing Re power alpha minus 1, rest all terms as it is. In the next step, what I am trying to do, I am taking f common from the two terms in the right hand side. So, then I have this expression. So, that is f is equals to 16 by Re divided by this particular expression. Now, here what I can write d tau of divided by v mu naught, I am writing some dimensionless number EL. So, then this is what we have. So, what you understand here, like Newtonian or power law fluids, the friction factor is not explicit. It is not explicit. So, you cannot get directly by substituting Reynolds number etc., or power law index, power law behavior index etc. Okay. So, it is a trial and error basis. Okay, that is what we understand here. So, this EL is nothing but d tau of divided by v mu naught, this is what we have. So, F RE by EL, if you further try to substitute and then try to write in terms of tau W something like that, F is nothing but tau W by half rho V square, and then RE is nothing but dV rho by mu naught, and then EL is nothing but d tau off by V mu naught. So, now here what we can see, this V, this square of this V, and then this V is cancelled out, this D is cancelled out, rho and rho cancelled out. So, what you have 2 tau W by tau off, because this mu naught is also cancelled out. So, F RE by EL we can write in the previous equation as 2 tau W by tau off. So, then F we can also write like this, right. Anyway, tau W again we cannot say that now equation for friction, now again we cannot say that the friction factor is explicit, because now we brought right side in form of tau W etc. No, because tau W is again related to F. It is just writing in a simplified form only, we are writing this one. Okay. So, still the F is not explicit, it is based on the trial and error approach only you can get the solution. So, now before concluding today's lecture, we will have a example problem. So, one fluid rheology is expressed by LS model fluid with mu naught is equals to this value, tau of this value, and then alpha 2.8. What we are asking, the pressure drop required to maintain a volumetric flow rate of 4 centimeter cube per second through 50 mm diameter and then 20 meter long pipe. L is given, D is given, Q is given, and then it was told that flow, assume the flow to be laminar, right. So, everything is given except minus delta P by L in the case of volumetric flow rate. In the case of volumetric flow rate expression, now here it is in terms of tau W is again minus delta P by L capital R by 2 or capital D by 4. So, this equation except the tau W everything is given. So, you substitute all those numbers here and then get the tau W information, and then from there tau W information use this equation to get the minus delta P value. Okay. So, but solving this equation, when you substitute all these values, you will not get straightforward. This will also include trial and error approach. When you do this one, you get tau W is equals to 3412 pascals, right. And then when you apply tau W is equals to minus delta P by L R by 2 expression here, and then substitute for tau W, R, and then L etc. here in this equation, what you get remaining minus delta P, you can get it as 5.4 megapascals. Okay. In the next class, what we try to do, we will be trying to obtain the similar expression if the fluid is viscoplastic fluid. That is what we are going to do in the next class. The references for this lecture, the entire lecture is prepared from this reference book. However, other reference books are also given which may be useful. Thank you.